Welcome, my friends! We talked in a previous video about investments that earn some flat percentage rate of interest. For example, we might have a $2,000 investment that earns 6% interest per year compounded annually. We could set up a function a equals 2,000 times 1.06 to the tth power to model the worth of the investment after t years. This is the case where interest is calculated once per year, commonly referred to as compounded annually. But a lot of the time, interest is not calculated once per year. It is calculated multiple times per year. For example, maybe instead of compounding annually, the interest was compounded semi-annually, meaning twice a year. If we go with the same example, the way it works is, instead of getting the whole 6% interest once a year, you get 3% every half year. Now you might be wondering, what's the difference? What do you think? Is 3% interest twice a year the same thing as 6% once a year? Well, no, not quite. Getting 3% twice a year is slightly better than 6% once a year, as it allows you to earn interest on the interest that you already earned in the first half of the year. Take our same example. 6% annually compounded interest on a $2,000 account after 1 year would be worth 2,000 times 1.06 to the first power, which comes to 2,120. 6% semi-annually compounded interest on a $2,000 account after 1 year would calculate the interest twice, 3% at the half year and another 3% at the end of the whole year, leaving us with 2,000 times 1.03 to the second power, which equals $2,121.80. Slightly more than the annually compounded interest. So you can see, if you are investing money, it is beneficial to have more compound periods per year. The number of times interest is compounded per year is represented by the letter n. The most common compounding periods are annually, which is once a year, semi-annually, which is twice a year, quarterly, which is 4 times a year, monthly, which is 12 times a year, and daily, which is 365 times a year. There is also something called continuous compounding, which we will talk about later in this video. Just to make sure you understand the idea, daily compounding on a 6% interest rate earns 6% per year, but split into 365 days, so that you actually earn 6% divided by 365, which is about 0.0164% interest per day. Wow! Due to the complexities of compounding, mathematical geniuses have come up with a formula to find the future value of an investment in a compound interest account. The formula is A is equal to P times 1 plus R over N to the N times T power, where A is the amount of money at the end of some specified period of time, P is the initial amount in the account, sometimes called the principal, R is the annual interest rate in decimal form, so the interest rate per year, N is the number of compound periods per year, as we have discussed, and T is time in years into the future, that you want to know the balance of the account for. If you look closely at the formula, you'll see that it makes a lot of sense with what we've already been talking about. R divided by N is just the interest rate per compound period. That's kind of like our 3% in the semi-annual compounding problem, which we got by taking 6% and dividing by 2. But we have to have 1 plus that amount, so that it's something like 103%. Then we raise that to the n times t power, which is just calculating the number of compound periods there are in your entire length of time, how many times interest is being calculated. For example, if we had 3 years, that would be 2 times 3 equals 6 half-year periods if you were compounding semi-annually, which is what the n times t calculates. Let's look at some examples. Suppose $2,000 is invested into an account that earns 4.5% interest compounded quarterly. Find the amount of the account after 6 years. Let's begin by just writing down all the information that we know. P is equal to 2,000, as that is the principal or initial amount in the account. R is the annual interest rate of 4.5%, which we need in decimal form, which is 0.045. N is the number of compound periods per year, which is 4 since we are compounding quarterly. T is equal to 6, as we want to know the balance in the account after 6 years. From here, it's as easy as plugging into the formula. We have A is equal to 2,000 times 1 plus 0.045 over 4 to the 4 times 6 power. We can type this all into our calculator. We have 2,000, open parentheses, 1 plus 0.045 divided by 4, close parentheses, raised to the 4 times 6 power, which gives us 2,615.98. There will be $2,615.98 in this account after 6 years. Let's try another one. Suppose $3,900 is deposited into an account that earns 8% interest compounded monthly. How much will be in the account after 11 years? Well, P equals 3,900, R equals 0.08, N equals 12 since we are compounding monthly or 12 times per year, and T equals 11 for 11 years. Plugging everything in, we have A is equal to 3,900 times 1 plus 0.08 over 12 to the 12 times 11 power. Plugging this into the calculator, we have 3,900, open parentheses, 1 plus 0.08 divided by 12, close parentheses, raised to the 12 times 11 power, which is equal to 9,375.09. There will be $9,375.09 in the account after 11 years. Okay, it's time to discuss continuous compounding. What if instead of earning interest every year, or every month, or every day, we actually earned interest every single moment, continuously? You might think that would mean your interest would be infinite. If you are constantly earning interest, wouldn't the amount just explode? Well, not really. Recall that with semi-annual interest, you had to divide the annual interest rate by 2, which was the value for n in the formula. For quarterly, you had to divide by 4, monthly by 12, yearly by 365, etc. That meant as n got bigger and bigger and bigger as the number of compound periods per year increased, that meant our interest rate per compound period, r divided by n, got smaller, as n is in the denominator. Well, for continuous compounding, the number of compounding periods per year, n, actually approaches infinity. Let's look at a slightly stripped down version of the compound interest formula. 1 plus 1 over n to the nth power. It turns out if you plug in really big values for n into this formula, representing more and more compound periods per year, you will start to approach a certain number. Plugging in 2, you get 2.25. Plugging in 4, you get 2.4414. Plugging in 12, you get 2.613. Plugging in 1,000, you get 2.7169. Can you guess what value these numbers are approaching? If you said E, you are correct. E is the constant equal to approximately 2.7183. And as n gets larger and larger and larger, this quantity approaches E, which is sort of a remarkable fact. Now remember again that the compound interest formula had a few extra parts to it. We have A is equal to P times 1 plus r over n to the n times t power. It turns out that if you let n approach infinity here, you will get, well, P out front, which is no surprise, but the whole parentheses is replaced with E, and then E needs to be raised to the r times t power. This is the formula for continuous compounding. A equals P times e to the RT, or A equals PERT for short. It turns out this formula works not only for interest, but also for other continuous models, such as continuous radioactive decay or continuous radioactive growth. Let's try one example using our new formula. Let's say some amount of money is placed into an account that earns 1% continuously compounded interest, and after 3 years, it grows to $3,039.84. How much money did the account start with? Well, let's write down the given information. A equals 3,039.84, which is the value in the account after 3 years. R equals 0.01 for our 1% interest rate. T equals 3 for the 3 years. Plugging into the formula, we have 3,039.84 is equal to P times e to the 0.01 times 3 power, which we need to solve for P, the initial amount in the account. All we need to do is divide each side by e to the 0.01 times 3 power. We have p is equal to 3039.84 divided by e to the 0.03 power, since 0.01 times 3 is 0.03. Plugging into our calculator, we have 3039.84 divided by e to the 0.03 power, which is equal to 2,950 if we round to the nearest cent, since 0.999 rounds us up. $2,950 must have been invested in order to earn $3,039.84 in this account after 3 years. Alright my friends, that wraps up our video relating to compound interest.